This is Miller's planet, the closest celestial body to the fictional black hole Gargantua. What makes this scene so remarkable? Well, within the mere 5-second clip from this planet, an extraordinary amount of time elapses on Earth, quite an astonishing occurrence. The pivotal concept here involves the time dilation effect, where spending an hour on this planet results in 7 years passing on Earth. How does this seemingly impossible phenomenon occur? In this video, we'll delve into the intricacies of time dilation, particularly as it relates to the events in Interstellar. We previously covered the foundational aspects of this topic in our video on Einstein's theory of relativity, which you can find here. To recap briefly, when influenced by a strong gravitational field, time decelerates. Therefore, near massive objects, time moves slower. However, gravitational pull isn't the sole factor influencing time dilation. According to Einstein's theory of special relativity, time also slows down for objects in motion. Combining these principles leads to an intriguing scenario. Let's envision ascending a flight of stairs. As we move away from Earth, we should theoretically experience time moving faster due to being farther from the gravitational pull. Yet, simultaneously, our motion while climbing should slow down time. Hence, being farther from gravitational influence causes our clock to tick faster, while movement counteracts this effect. Naturally, this is a simplified explanation, and the complexity lies in the specifics. However, our focus remains on comprehending time dilation and its implications. Let's explore a scenario involving two individuals, Person A floating near a massive object with substantial gravitational pull, and Person B leisurely drifting in the void of space. Person A directs a green laser beam toward Person B, vibrating at a frequency of 600 trillion vibrations per second. Light, as a form of energy, undergoes alterations as it exits the gravitational influence of the massive object. This exit leads to a loss of energy within the beam, resulting in a decreased frequency by the time it reaches Person B. For instance, the once green light at 600 trillion vibrations per second might transform into approximately 10 billion vibrations per second, akin to a microwave radio beam. This phenomenon is termed gravitational redshift. However, the diminished frequency of light doesn't just vanish. Since Person A emits 600 trillion vibrations each second, while Person B only receives approximately 10 billion per second, a discrepancy arises. This disparity can only occur if 1 second for Person A does not equate to 1 second for Person B. In essence, while it takes 1 second for Person A to emit 600 trillion vibrations, it could take Person B nearly a day to receive them. Consequently, the discrepancy in the rates at which time progresses between individuals leads to a remarkable difference in their experiences of time. Biological clocks, including heartbeats, breaths, and cognitive functions, tick at divergent rates for each person. What feels like a few seconds to Person A appears as slow-motion observation to Person B, with significant intervals elapsing between events. Revisiting the scene from Interstellar, this explanation provides insight into why Cooper mentions that he might be the same age as his daughter upon his return from the mission. This disparity in the passage of time becomes apparent, creating a significant time differential between individuals in distinct gravitational environments. Now, delving into Einstein's special relativity, it establishes that the greater the acceleration of an object, the slower it moves through time. On Earth, where time experiences a minimal slowdown of just a few microseconds per day, the gravitational pull is moderate. In contrast, a neutron star's surface, experiencing a few hours of slowed time per day, exerts immense gravitational force. At the surface of a black hole, time virtually ceases due to the colossal gravity, preventing anything, not even light, from escaping. In the context of Interstellar, Miller's planet, situated close to the black hole Gargantua, experiences extensive gravitational pull, resulting in a significantly slower passage of time. Meanwhile, on Earth, gravity operates at a moderate pace, about 1 billion times weaker than Gargantua's force, causing time to progress comparatively faster for those on Earth than for the 3 astronauts on Miller's planet. And of course, all of this information is brought to you from the book, The Science of Interstellar. Authored by the scientific consultant of the film, this phenomenon manifests in various locations across space and reality. An intriguing instance is exemplified by our very own International Space Station, ISS, where time unfolds at a slower pace than here on Earth. In technical terms, it operates under a distinct time frame compared to our own. By employing Einstein's equations to compute this variance, we can rectify the temporal aspect at the ISS. And equivalence emerges. 1 second on Miller's planet translates to 1 day on Earth. Drawing inspiration from the movie Interstellar, let's delve into a specific case study that demonstrates how the filmmakers created the sensation of time dilation. The initial sequence unfolds as Cooper and his team set foot on Miller's planet, accompanied by an intense musical score infused with clock-like ticking elements. The tempo of the music undergoes alterations throughout the track, symbolizing the impact of time dilation due to the planet's proximity to a singularity. For every 60 seconds of the musical track, there occur 48 ticks of the second-hand sound. According to the movie's premise, an hour spent on Miller's planet is equivalent to approximately 7 years on Earth. Let's engage in some calculation to illustrate this concept. An hour encompasses 3,600 seconds, and a day comprises 24 hours. To achieve a span of 7 years, we calculate by multiplying the seconds in a day by the days in a year and then by 7, resulting in an approximate total of 221 million seconds over 7 years. This computation establishes a conversion ratio of roughly 61,400 Earth seconds for every second spent on Miller's planet. When this figure is multiplied by the time interval between each tick, it yields approximately 77,000 Earth seconds, which equates to about 21 hours. Thus, each audible tick signifies nearly a full day passing on Earth. This stark contrast illustrates the simultaneous unfolding of events on Miller's planet and Earth in real time. However, delving into this extreme time dilation raises pertinent questions about its plausibility on such a planet. Could human beings even walk on its surface? Although the film depicts the planet's gravity as 130% of Earth's gravity, evidenced by the actors visibly exerting effort due to the additional gravitational pull, this factor alone falls far short of inducing such substantial time dilation. In reality, even if one were to visit the surface of our Sun, a considerably massive celestial body compared to Earth, the time gained would amount to only about 66 seconds per year. Achieving the extreme time dilation portrayed in the movie, where an hour corresponds to 7 years, demands a gravitational force akin to the event horizon of a black hole. No known planet possesses such intense gravity, and attempting to land on its surface would result in immense crushing force. The astronauts' weight would be several million tons, an astronomical figure even without performing precise calculations. Nevertheless, it's important to note that striving for scientific accuracy in a narrative like this would significantly limit the movie's enjoyment. Ultimately, Interstellar resides within the realm of science fiction rather than strict scientific realism. If you found this video informative, make sure to subscribe to our channel for more content.